Good morning. Today we will talk about the very important, but I'm afraid a little bit difficult to understand on first try, bridge dynamics. We had a first taste of cable dynamics some lectures ago, and today we will talk about what happens under wind to the beam mainly, but also, of course, to the towers. Now, a regular bridge engineer, as I like to call myself, does not do the detailed aerodynamic investigation for a bridge design himself. He has a specialist who does that for him, but we as engineers should be able to understand what these specialists are telling us. We do not have to do the calculations ourselves, but we must understand what we are talking about. And that is the aim of the lecture today, to make you understand what various phenomena, dynamic phenomena, have to be investigated by the specialist and what he tells us about the different things. I've been working in the United States with famous aerodynamic specialists, Alan Davenport, Bob Scanlon, who found new ways, but for all the other bridges outside the US, I've worked with my very long-time colleague and friend, Dr. Imre Kovac, who was kind enough to write the script for this part, taking in mind that he's a world-known, worldwide specialist, and I've listed here most of the cable stay bridges he did the aerodynamics on. So I try to tell you what I have learned from Dr. Kovac. We will go in the first lecture basically through the basis, wind effects, wind profile, and so on. And then we talk about vortex, we talk about self-excitation, buffeting, and so on. You will see that one after another. In the early times of bridges, the aerodynamic phenomenon, aerodynamic excitation in the widest margin, was not understood at all. And so what happened was that many of the larger early bridges, especially of course suspension bridges, failed due to wind. And look here, from 1818 to 1940, well known, or you have heard Dryburgh Abbey, one of the first cable stay bridges in England, I told you in lecture 2. You may have heard The Bridge on the Tay by Theodore Fontane. When shall we three meet again? The Witches from Macbeth starts his poem. And of course, technically very important, the Tacoma Narrows Bridge, a major bridge which failed in 1940. And Tacoma was the reason why aerodynamic effects have been investigated scientifically. Until then, it was touch and go and try out and understanding. People stabilized suspension bridges with additional stays, things like that, but it was all by feel. The University of Washington, which is close to Tacoma. Tacoma is somewhere near Seattle in the state of Washington. Started that under Professor Farquharson, and then he found, okay, the problem of flutter, one of these phenomena, but a very important one, was solved for the wings of airplanes by Theodorsen, theoretically. And then the Austrian engineer Friedrich Bleich used his calculations for bridges. And in Germany, Klöppel and Thiele then applied the rather complicated Friedrich Bleich calculation method to something which regular engineers could handle. We will see that later, and that made it in Germany, in the 1965, I think there was a publication by Klöppel-Thiele, suddenly available also, say, in Germany, to do these calculations. So it all started with Tacoma. And to my amazement, in former years, I found out that you had never seen the famous movie how Tacoma Bridge in wind failed. I will show it to you again today. At that time, it was one of the largest bridges.
Steel girders, 8 feet tall, which were supposed to stiffen the bridge against the bending. However, some up and down vibration was observed during the entire useful life of the bridge.
Which was rather short.
Here's opening day.
Since the bridge moved from the very beginning in the wind, it was investigated by the University of Washington,
Suddenly went into a twisting motion.
and there was a movie camera to film that disaster.
The bridge oscillating in one of its natural modes of vibration with a period of 5 seconds.
Torsional galloping. You will hear about it later. But it's a real effect. It's nothing theoretical. Bridges can fail.
Went out to see what had happened. He's coming back, walking with some difficulty along the nodal line, which is the center stripe of the wing blade.
It's pumping more and more energy out of the wind flow into the bridge.
With this flexible. This is photographed at normal speed. However, the collapse was inevitable after a little more than an hour of this.
And now the movement grows and grows beyond theoretically any limit, also, of course, beyond the structural strength.
Had been abandoned earlier. No one was injured in the whole affair. However, a small dog in the car was frightened and was afraid to come out, and he perished along with the bridge.
Okay, now, here we have seen what wind can do to a bridge
Rebuilt using a stiffening truss instead of girders. The new bridge is completely stable.
So we have to take great care that this doesn't happen to our bridges. It's a real problem we are dealing with, not just some theoretical considerations. It's real. Now, we start with an overview of the wind effects. This is a very important slide, which we will show again, and you should try to remember. We have three different phenomena. We have turbulence, we have vortex, and we have what we call motion-induced, what we just had this moment. Now, turbulence-induced comes from random fluctuations of wind and wind speeds, just gusts, cause the bridge to move if it hits in the right moment. The next one is periodic vortex. Vortices form behind a bluff body. Theodore von Karman found that out. And this periodic vortex shedding creates small forces, but with time they can also excite the bridge. And the third, and the really dangerous one, are the motion-induced, where we have a working together with the bridge itself, the bridge beam, and the surrounding air. They work together as a unit, thereby changing some characteristics of the bridge beam, be it the frequency, be it the damping. And this phenomenon, for example, Tacoma, then is like a stability problem which we have in buckling. The movement of the bridge can go beyond all limits and can destroy the bridge. So, turbulence, vortex, and motion-induced, we say here. We start with the general idea of what is the wind, how do we define the wind. We have basically two characteristics. That is the wind speed at 10-meter height, which is given by codes or which has been measured on a remote side. And we have the turbulence intensity, meaning that the wind is not just steady, laminar, as we say, but it has gusts. And the percentage, these gusts have a higher speed than the average speed. That is what we called intensity. And the function from zero wind speed, of course, at the ground to somewhere high air constant is basically an E function which it goes up. So wind speed at any height is a function of the 10-meter height speed plus this factor which shows the run of the wind speed up. It all depends a little bit on the roughness, and in addition to these two, 10-meter speed and the turbulence intensity, we must consider the probability how often a wind speed occurs. And it's clear if we want to know the highest wind speed in a 100-year period, that's much higher, which, for example, should be for the life of the bridge. We normally assume 100 years. But we have shorter erection stages, and there the probability of a high wind speed occurring is smaller. So typically in German codes, if we don't know any better, we use 42 meters per second in the final state and 30 meters per second during construction. Of course, there is no guarantee that the 100-year probability will occur during construction, but then the factor of safety must come in. So we have on one hand the wind blowing onto the structure, on the other hand we have the structure itself reacting to the bridge. And the most important reaction are the natural frequencies or eigenfrequencies. The most important is the vertical bending, which typically is here 0.25 Hertz, and for the dynamic effects motion induced, maybe even more important, the torsional eigenfrequency, and especially the ratio of torsion and torsional frequency to bending frequency is important. We should have at least 2 or even more to make it safe. If we have vertical tower legs and an open cross-section, then the ratio of torsion to bending is just, as a first approximation, the distance to the cable plane to the torsional radius of inertia, where thereby we neglect the torsional inertia of the beam itself. So that's a very general assumption. Different it is if we have an A-tower. An A-tower increases the torsional frequency of the beam. How that? We've mentioned it, we've calculated it, but I show it again. If we have a torsional movement of the beam and we have vertical tower legs, then the tower legs go this and that. Now, if we combine the tower legs, they can't move independently, which means we take out the cable elongations of the backspan, and thereby we increase the torsional frequency. And this example here shows that we have on one hand the 0.896 to 0.395 frequencies, which gives a ratio of 2.27. However, what I showed you on the last slide, if we just take the beam itself, that would come to only something 1.5. So we have an increase by 50% in torsional frequency by using A-towers instead of vertical towers. Third possibility, if we have a center tower and one cable plane only, well, then the torsional stiffness and the torsional frequency as a consequence comes from the torsional inertia of the beam. That means when we can have open cross-section with virtually no torsional stiffness itself for 2 cable planes, where the force couple in the 2 cable planes prevents rotating of the beam, then here we need a closed box, which we have here, and the torsional frequency is virtually independent of the stay cables, because the stay cables act in the middle and they are not strained at all. So it's the torsional frequency of a box girder with the main span length, which gives the torsional frequency. And then the bending frequency is similar. That's not influenced whether we have 1 or 2 cable planes. So in this case also we have a ratio of 2, which sounds reasonable to start with. Okay, now we now come to the first of the 3 phenomena, turbulent excitation, which means we have the bridge standing in wind and the wind blows with gusts, stronger and less strong. And by that, more randomly, moves the beam, and by moving the beam, of course, strains and stresses are originated, which, like any life load or so, we must calculate and ascertain, assure that these do not go beyond the permitted limits. As I said, turbulence induced, just the wind gusts blowing and moving the bridge randomly. Well, what forces are exerted by the wind onto the bridge beam? If we can measure that when we put such a beam into the wind tunnel and then let the wind blow at different angles against it and measure the resistance, the force, which is exerted onto the beam. Well, first of all, we have the horizontal, the drag. That's rather, that's 0.2 times, it's always the width. It's more or less constant for wind angles of attack, 0.2 something. Then the wind tries to lift or push down the bridge. That coefficient, of course, changes strongly with the wind. If the wind blows from below, it tends to lift it up. If the wind blows down, it tends to the other way around. And in third way, we have a torsional moment varying with the wind angle of attack. So we have these three forces acting on the beam from wind, very important. We have the horizontal, the drag, we have the vertical, the lift, and we have the torsion. For, say, sizing of a bridge, not mainly we look into drag, but for their dynamic phenomena, all three are equally important. One way, one possibility to calculate the forces under turbulent wind is to place a model, part model, section model, into the wind tunnel, dynamically on springs supported with the same eigenfrequency as the real bridge beam, of course scaled. We see that later a little bit on wind channel. And then we can measure how the beam moves. For example, horizontally, we have here the wind speed increasing, and here we have the vertical movement, lift, and here same wind speed increasing, and we have the rotational angle. And when we have these values corresponding to the wind, we can backwards calculate what equivalent statical loads would produce the same deflection of the bridge which we have measured in the wind tunnel. And that can be, for example, for the base average mean speed, a constant transverse load, and then for the vortices, a variety of additional dynamic loads. And there we will have a great number of loadings, and we will get an envelope of moments, and from that we can calculate the stresses. That's basically Davenport's method. Now, there is today more sophisticated method, which Kovacs, for example, has developed. And that uses an analytical method. On one hand, the wind field with the gust characteristics as defined is created in the computer. That's this one here. And then we let this wind blow onto the bridge, which we have a bridge model in the computer with the proper frequencies and so on. And we use the results from the wind tunnel with the part section model to find out, let the computer find out, what forces, lift, drag, moment, are exerted from this wind onto this structure. And then, I come to the film in a moment, as a result we can directly, from the computer, get the moments out of that. So we don't have to recalculate backwards, forwards, but do it all by computer. And we show now a film how this was done by Kovac for the Helgeland Bridge, which was an extreme wind climate. Here we see, first of all, just the generation of a wind field with the same mean speed and turbulence characteristics. It's a time history method, and there are normally 10 runs of a certain period of time which give all the variety mathematically which can be in this wind field speed and gas distribution. These are just short periods of time from various time history runs. Okay, and now we see the bridge as a computer model hit by this wind field using the lift, drag, and moment factors which were exerted from the wind tunnel. Later, with the Incheon Bridge, I will show you an example where we can also find the beam coefficients analytically. There, we don't need a wind tunnel at all. Here we have the wind tunnel in to get these characteristics out and apply them to the bridge. And here you see the movement of the bridge. I think that should do it. Now, the computer can now give us a moment envelope, biggest moment at any place from all these, say, 10 time history runs, and we can introduce nonlinear characteristics into the beam. For example, if we have cracked concrete, the stiffness goes down and the frequency changes, but the moments are also reduced. And so all this has been done here with the Helgeland Bridge. And so we have here the phenomenon that we have the first order and we have the ultimate stage with cracked and uncracked section. And so it can come up that due to the cracking and reducing of restraint moments, the nonlinear or second order moments are smaller than those linear with uncracked sections. So this is an excellent result which enables us to check, okay, the wind stresses are not bigger than those from live load are within the permissible range. Now, the next one we talk about is vortex. Now, vortex induced, we have a regular vortex shedding, and if the frequency hits the beam frequency, then if it's in phase, if it's resonant, then we may have a rather big movement. Now, what happens? If we have a wind blowing on a pipe, then we have this shedding of vortices upwards, downwards, upwards, downwards, and the frequency is defined by the Struhal number, wind speed divided by the characteristic depth or width times Struhal, 0.2 for a pipe, And we see it there, for example, at lamp standards, where we just have this size of steel pipes holding up a lamp on a parking lot or so. And there you can sometimes see that it vibrates, that vortex, that's vortex shedding. Now, if we have a bluff bridge beam, a through hull is about that, in that range. And there is a certain effective force from the wind speed for through hull, this up and down, that factor is something like 1.1. And over the vortices do not form uniformly over the whole length of the bridge, but they have a local length which is somehow somewhere 6 times the characteristic depth. So it's acting here, but not uniform. And so we can then calculate these drift forces upwards, downwards from vortex shedding if we have the frequency of the beam, the vertical bending, in phase with the vortex shedding. Now, thank God, I would like to say, what shines up in the wind tunnel not always appears in reality. We have here a typical diagram from a wind tunnel where we have increasing wind speed up to probably 70 meters per second, probably for reality already recalculated. And here we have the movement. And we see here for a rather low wind speed, very typical, in the range of, say, 15, 20 meters per second, which is something like 40, 50 kilometers per hour, we have a rather big vortex shedding, because here the frequency of the vortices coincides with the natural frequency of the beam. So we have rather big movements, and much further on we then come to aeroelastic flutter or torsional galloping. Now, this not always shows up in reality, and that has to do with the so-called Reynolds number. Reynolds number is defined wind speed times characteristic depth divided by the kinematic viscosity, which is a constant. And the wind speed 10 to the power of 5, Reynolds, distinguishes whether we have laminar uniform flow, where all the, say, air molecules flow in parallel, or above 10 to the power of 5, we have turbulent, where they all mix up together in the flow. And vortex shedding only takes place with laminar flow. And so, in reality, we do not have this regular flow very often, and we have not perfect shedding frequency because the wind does not blow all the way constant. This is a comparison. If we would have perfect wind blowing constant, we would have, in resonance with the beam frequencies, we would have these movements of the beam. In reality, even in the model, this was measured for a realistic wind much smaller. So don't get all excited when you have a resonance phenomenon in the wind tunnel. Just consider carefully, maybe it will not show up in reality. And with my bridges, that always happened. We never had to do some special damping or so for vortex shedding, although the wind tunnel showed up that there may be a problem. But it's the difference between real wind and wind in the wind tunnel. Now, this was our first lecture where we investigated the first phenomena, turbulence and vortex. The next part we will go into the real dangerous one, which is the dynamic self-excitation.